we're given the expression series infinity n equals 1 over square root n plus 4. So we are asked to determine whether the series converges or diverges and justify our answer. So I'm going to be performing the integral test. The integral test states that the integral of any a sub n from 1, as long as it starts from 1 and goes up to infinity, and that it decreases the entire time monotonically, will be the same, will both diverge or converge with the original a sub n series. So let's find the derivative of this. So f prime of x. So we have f of x is equal to x plus 4 power of 1/2. Negative 1/2. Multiply that in front, negative 1/2 in front, x plus 4, and then negative 3/2 as the exponent. This gives us a negative in the front, and so the expression will always be decreasing. We already know it will be starting from 1 always, because it starts at 1 in the series. So it forces it to 1. So I'll now perform the integral test. So now the integral from 1 to infinity of 1 over square root of n plus 4 dn. So we're going to make u is equal to square root of n plus 4 du. Already have that. It's going to be negative 1, just 1/2 square root of n plus 4. And in fact, this is not a square root. This is actually 1 over the square root of n plus 4. So now we can solve for dn. So we just end up having dn is equal to 2u, because we divide a negative exponent, making it positive. So now that we have that, leave that up here, dn equals 2u. So now that we have that, read out over here, u equals square root of n plus 4. dn equals 2u is this one over here. So now we can rewrite the integral as infinity of 1 over u to u du. The u's cancel out, and so we integrate just 2. We end up with just as u, end up with 2u from 1 to infinity. So now we can plug it back in, 2 square root of n plus 4. And now that we have that, we can do the limit test on this, because this is in, we can just 1 to infinity, and then so you have a limit n approaches infinity of 2 infinity. So this all turns into, the limit as 2 approaches n plus 4, which this is all infinity. And then if we plug in 1 minus 2 square root of 5. So infinity minus 2 square root of 5. And that's just equal to infinity. So the entire thing diverges. So we are given the expression, the series to infinity, n equals 1 of e to the power of n all over n squared. So we're going to be performing the nth test. This basically says that the limit of any a sub n, as long as it's greater than 0 or not equal to 0, it will diverge. So we're going to take the limit as n approaches infinity, e n squared. This is equal to infinity over infinity, which is indeterminate. So we can't do that. So we're going to do L'Hopital's. To get e to the n all over 2n. Again, this gives us infinity over infinity when you take the limit to infinity. We're going to do L'Hopital's one more time. This is e to the power of n over 2, which gives us infinity. So now that we know that the limit as n approaches infinity, a sub n is equal to infinity, which is not equal to 0, we're able to say this all diverges. So we are given the expression series to infinity, n equals 1 of n plus 1 all over n square root of n. So we are going to perform the direct comparison test. So to do the direct comparison test, we need to compare we have to basically shove out divergency in this case. So we're going to define our expression. So we're going to say n all over n square root of n is going to be our comparison. B sub n is equal to this. So now, as you can see on B sub n, we're able to cancel out these two n's, first of all, and we are left with 1 over square root of n. It's all still b of n. So B sub n diverges by p series, because our square root, which is the same as saying n to the power of 1/2, because our p is less than 1, the entire series will diverge. So will our a sub n. So we're given the expression series to infinity n equals 1 of 3 all over n times n plus 3. So the first thing I'm going to do is I'm going to decompose the fractions within these. So I'm going to say our a sub n is the same as saying 3 is equal to constant a, n, plus b, side n plus 3. It decomposes. So, basically when n equals 0, means, let me put this entire little expression in red. So when n equals 0, we end up seeing 3 equals 3b. So dividing both of them out, b equals 1. So now isolating our a when n equals -3, then we end up with 3 is equal to -3a. Cancel these two out. End up seeing that a is equal to -1. So this side a equal to -1, b is equal to 1. So erase all this. So now, let's see. RB, actually hold on, erase too much there. Erase that top expression. So we end up saying that this entire a sub n is equal to 1 over n minus 1 over n plus 3. And so we can use the telescoping. This seems to be a telescoping method because we end up having two expressions, this one and this one, that end up being opposing each other, canceling themselves out. So we need to find the first couple terms that don't get canceled out by this entire expression. You can see that there's a shift of 3. So we know that because there has to be a shift of 3. And the first 3, so that means when n is equal to 1, 2, and 3, they will not be canceled out by this expression because we start at 1. So I'm going to find those a sub n's. So I'm going to find when 1 over n is equal to 1, 2, and 3. So this is 1 plus half plus 1 over 3. You're getting 3 halves, plus 1/3. Then they're cross multiplying, and getting 11 over 6. This converges to 11 over 6 by telescoping. Converges.